Let's consider an object that starts off at point P, where the time is 0, the position is x naught, and the velocity is v naught x. And the object is going to move from point P to point Q. And it's going to do this with a constant acceleration. When the object arrives at point Q, the time is t, the position is x, and the final velocity is vx. And what I'd like to do is to take this type of motion and determine a few equations we call the kinematic equations, that can be used for situations like this. Situations where the object is moving in one dimension with a constant acceleration. So I'd like to start with the definition of average acceleration. And that is something like maybe the acceleration in the x direction is equal to a change in velocity divided by a change in time, delta v over delta t. And so for this object between points P and Q, the final velocity is vx, the initial velocity is v naught x, the final time is t, and the initial time is 0. So delta anything, whether it's delta v or delta t, is always the final value minus the initial value, or here the value at point Q minus the value at point P. And so since the initial time was 0, this could also be written as vx minus v naught x over t. And this could be rearranged for the final speed. So the final speed, vx, is equal to the initial speed, v naught x, plus the acceleration times the amount of time between points P and Q as the object was moving. And this is one of the three kinematic equations that I'm trying to derive in this video. If you know some information about how the object is moving, you can determine the final speed of the object. Or at least that's what I've solved the equation for here. The next equation that I would like to determine is an equation for the final position. And so for this equation, I would like to start with the equation for average velocity. And so average velocity, Vx, maybe there should be a bar over that to indicate that it's an average quantity, is in general delta x over delta t. So here the final position is x and the initial position is x naught. And again, the final time is t and the initial time is 0. Here, since I'm deriving equations, I'm trying to use the most generic variables that I can. And again, in this case, this can be written as x minus x naught divided by t. I also know another fact, and this fact is going to help me derive this second equation. And that is, if the object is moving with a constant acceleration between these 2 points, and if and only if it moves with a constant acceleration, then I know that the average speed between points P and Q is also equal to the initial speed plus the final speed divided by 2. If I want to find the average of something, I add up all of the values and I divide by the number of values. So here I take the initial value, the final value, I add them up and divide by 2, and I get the average value. And that's only true if there's a constant acceleration. But now what I've done here is I've created two different expressions for the average velocity. And now what I'd like to do is set those equal to one another. And so I'm going to set this equation here equal to this one here. And so that would look something like this, right? V naught x plus Vx divided by 2 equals x minus x naught divided by t. There's one more substitution that I would like to make, and that is to get rid of this final velocity in the equation and instead replace it with the expression that we found up above. So Vx equals V naught x plus Axt was the first equation that we derived, and I'm going to substitute that in for Vx in this expression that I have here. So that gives me V naught x plus V naught x plus Axt divided by 2 equals x minus x naught divided by t. And so now with a few steps of algebra, we should see that the expression I have is 2 v naught x plus ax t divided by 2 equals x minus x naught divided by t. And so if I solve this for the final position, so this is the last step, solving for the final position, I can cancel the 2's in the first term on the left-hand side, I can multiply both sides by t, and then I can add the initial position to both sides. And if I do all of those steps, then the final equation that I'll have is x equals x naught plus v naught x t plus 1/2 ax t squared. The last equation I'd like to derive is just as important as the first two, but it does take a little bit more math in order to arrive at that third equation. And so what I'd like to do is I'd like to clear the screen. But let's call this first equation that we found equation number 1, and we'll call this second equation that we found equation number 2. And for the third equation that we are going to find, it is an equation that does not have time in it. If you look at these equations, you'll see that there are positions, there are velocities, accelerations, and time. And the third equation will be an equation that does not require you to have any information about the amount of time that it takes between 2 points. And so what we'll need to do is take these first two equations and eliminate the time variable. And the way that that's going to work is ultimately we are going to take our first equation and solve it for time, and then we are going to substitute that expression into these places in equation number 2 where we see t again. And that will eliminate the variable, and then ultimately we will simplify that expression. As I just said, we're going to take equation 1 and solve it first for time. So t equals vx minus v naught x divided by ax. And now we're going to substitute that expression for time into the two places in equation number 2 where we see t. And so this looks like the following: x equals x naught plus v naught x times the expression we just found, vx minus v naught x over ax, plus 1/2 the acceleration times this quantity squared that we just found, so vx minus v naught x divided by ax again. And so now this equation is quite a mess, but there's a lot of simplification that can happen from here. And so the first thing I'm going to do is in the second term, I'm going to distribute this v naught x into the two terms, but then I'm going to separate those two terms apart. And so I'll have x equals x naught plus v naught x times vx divided by ax minus the second term, which would be v naught x squared divided by ax. And now looking at the third term, I have a plus 1/2 ax out in front, and I have that whole quantity squared. And so what I'd like to do is I would like to take just what I see in parentheses here, and I'd like to square what is inside of the parentheses before I make any moves with what is in front of the parentheses. So I'll start by writing 1/2 ax, and I'm going to FOIL the numerator. And when I FOIL the numerator, I have vx minus v naught x times vx minus v naught x, those two quantities. And so what I get as a result in that numerator will be vx squared minus 2vx v naught x plus v naught x squared. So that is that numerator FOILed out, first, outer, inner, last. And the denominator will just be ax squared. So of course one of these ax's will cancel, and then I could distribute the 1/2 into each of the terms and separate them in the same way that I did with the second term in this equation. And so that would look like the following. And we just have a few more steps here before everything will cancel out, leaving us with what is a quite useful equation. So x naught plus v naught x vx over ax minus v naught x squared over ax plus, and so now one of the terms of the acceleration will cancel, so ax will go away with this squared. And we will have the following terms. Vx squared over 2ax is the first term. Then the next one will be minus 2vx v naught x over 2ax. And the last term will be plus v naught x squared over 2ax. And now we should see that there are a few things that will cancel. First, we notice these 2's will cancel with one another, and that with that I have a plus and minus version of that term here and here. And so for that reason, both of those two terms will go away. I also see that I have a minus v naught x squared over ax and a plus v naught x squared over 2ax. And so minus 1 v naught x squared over ax plus 1/2 gives me a minus 1/2 of that type of a term. So I'll write x equals x naught minus v naught x squared over 2ax. And then I have that other term, which is not going to cancel, which is plus vx squared over 2ax. And so what I could do here is I could subtract the initial position to the left-hand side of the equation. I could multiply both sides of the equation by 2 times the acceleration, and then I'll have a relatively simplified equation. When I do that, what I'll end up with is, well, I'll write one more intermediate step. So x minus x naught times, I'm multiplying now both sides of the equation by 2 times ax, which means on the right-hand side I will just have minus v naught x squared plus vx squared. And if I rewrite this in just a slightly different way, solving it for the final speed, which is this term, then the equation that I've arrived at is vx squared equals v naught x squared plus 2 times the acceleration times the displacement, really, the final position minus the initial position. This is our third and final kinematic equation that we're going to derive here. And these three equations are extremely useful for trying to understand the motion of an object. They're each a little bit different. You'll notice that the third equation does not have a time variable. You'll notice that the second equation doesn't depend on the final speed of the object. You'll notice that the first equation doesn't have any positions in the equation. And so each one can be used for a different purpose. But you absolutely need to remember that these three equations can only be used in instances where the acceleration is constant. Because when we were deriving these equations, that was an assumption that we made, that the acceleration was constant. But if you are working a problem where the acceleration is constant, then these three equations can be extremely valuable. And so we need to get a little bit of practice using these. And so the last thing I'd like to do is to work an example using a couple of these equations. Here we have an example of two trains that are traveling toward one another. The problem reads, two trains are 950 meters apart when they see each other and both apply the brakes, causing a constant deceleration of 0.8 meters per second squared for each train. At the instant they begin braking, one of the trains is traveling at 32 meters per second and the other is moving at 38 meters per second. Do the two trains collide? If yes, when do they collide? And if no, how far apart are they when they stop? And so The first thing that I would recommend doing in any sort of a motion problem, especially when you're tracking the motion of two different objects, is to draw a picture and pull all of the information from the problem out of the problem itself. And so I'm going to draw a pretty crude sketch here of what this problem looks like. And it looks something like this. I'm going to say I have a train here, and this is train A, and it is going to be moving to the right. And then on the other side, here I have train B, and it is going to be moving to the left. So the two trains are moving toward one another. And I'm going to say that train A, which is on the left here, is starting off at an initial position of 0. So what I'm saying is that I'm going to have these two trains moving toward one another attached to a coordinate system that's going to help me solve the problem. So the 0 position on this coordinate system is right here where train A is. And since the two trains are 950 meters apart, that's fine. I can say that train A is at 0 as long as I say that train B has an initial position of 950 meters. And so what I've just said, if I'm calling the initial position of train B positive 950 meters, is I'm declaring that the positive x direction is to the right. So I've defined my coordinate system. And since these are trains, they can only move in one dimension. So I've got the positions. I should also indicate the velocities. The initial velocity of train A is 32 meters per second, and the initial velocity of train B is 38 meters per second. I also know that the acceleration of both of these trains, AX, is equal to 0.8, or at least the magnitude is 0.8. So 0.8 meters per second squared and 0.8 meters per second squared. Now we need to think about the signs a little bit, because velocities and accelerations are both vectors. And if both of these trains are on a coordinate system where there's a positive and negative direction, I need to indicate whether these vectors are positive or negative. So we'll start with train A. The velocity is positive because the velocity is pointing to the right. It's moving in the positive x direction. But the acceleration, which would cause this train to slow down, should be pointing to the left, opposite the direction of the velocity. Things slow down when the velocity and the acceleration are pointed in opposite directions. So the acceleration should very much be negative. And now for train B, the train is moving to the left, so the velocity is what should be negative. But the acceleration, even though it is causing train B to slow down, needs to be positive. And that's because the velocity is negative. In general, just remember that things slow down when the velocities and accelerations point in opposite directions. And they speed up when the velocities and accelerations point in the same direction. And so this is the initial moment in time, right, when they're 950 meters apart and they see one another and they begin braking. And we know that at some point later in time, we're not sure where these trains are going to be, but they're going to be somewhere in here. Maybe they've collided, or maybe they're just closer to one another. But there's some moment later in time where they are at different positions with different velocities, and so we should record what information we know about those positions as well. So I will say that the final position of train A, I'm going to call that XA, and the final position of train B, I'm going to call that XB. And part of this problem is understanding the relationship between XA and XB. If they collide, then the two positions would be the same. If they don't collide, then they might have different final positions. So for now, I'm just leaving them as an arbitrary variable, XA and XB. The final velocity of these trains, VF, is going to be 0 no matter what happens. And that's a pretty important insight. If the two trains collide, then they most certainly have to stop, but if they are able to stop before they collide, then they'd also stop. So the final velocity, no matter what happens, is going to be 0. And so now what I'd like to do is to take all of this information and use our kinematic equations to answer this question: do the trains collide? The information above is the exact information from the previous part of the video. I've just copied it so I have a little bit more room to work and solve this problem. So the question here is, do the trains collide? And so the way that I'm going to determine whether or not the trains collide is I'd like to figure out what the final position of each one of these trains would be if they were on separate tracks. So let's analyze the motion of each train independent of what the other one is doing. And the way that I'm going to do that is I'm going to use the equation, which I suppose we've been calling the third equation, Vx squared equals V naught x squared plus 2a times delta x, the displacement, x minus x naught. And so let's apply this equation to each train independently. So for train A, this equation would look like the following. The final speed is 0, so Vx is 0. The initial speed of train A is 32, so 32 squared plus 2 times the acceleration, and the acceleration is a vector, which is here minus 0.8. The final position of train A we do not know, that's what we're looking for, and so we'll call that XA, and the initial position was 0, so minus 0. 32 squared is 1024, and this second term, if I recognize the minus sign with the 0.8, will be 1.6 times XA, the final position of train A. And if I solve that for XA by adding 1.6 XA to both sides and then doing 1024 divided by 1.6, I'll find that the final position, XA, is equal to 640 meters. So in my diagram, if I wanted to take this crude diagram and now start to make it some sort of two-scale thing that's representing what's actually happening, then the 0 marker on my x-axis was here on the left, and the 950 meter position is where train B started, and so 640, that should be somewhere about 2/3 of the way toward train B. So maybe train A ends up being somewhere like right here, actually. And so now we should be able to do the same sort of thing for train B and figure out where along that timeline, or where along that position axis, it should be. And so now applying this equation to train B, the final speed of train B is also 0. The initial speed is 38, so that should be squared. And if I'm being careful, really this should be a minus 38. But since in this kinematic equation, since the velocities are squared, it doesn't really matter whether I knew if that was positive or negative. I then add 2 times the acceleration, which is positive for train B, times xb minus the initial position, which is not 0 for train B. The initial position of train B was 950. 38 squared is 1,444. 2 times 0.8 is still 1.6, so we have 1.6 xb for the first term, and then 1.6 times 950 is 1,520. So this equation could be solved for xb. And so if you solve this equation for xb, what you'll find is that the final position of train B is equal to about 47.5 meters. And so in the picture up above, the final position of train B is going to be quite close to where train A starts, maybe somewhere like right here, I'm not quite sure. And so what this means is, in order for train A to get to its final position, it needs to do something like this. And in order for train B to get to its final position, it needs to do something like this. So quite obviously, we see that if they were on separate tracks, the two trains would have to pass one another in order to get to their final positions. And this is assuming their initial speeds, the accelerations that the brakes on each one of these trains can provide. And so what this means is, if those two trains were on the same track, the brakes that they have do not provide a large enough acceleration in order for them to stop before they would hit one another. Now, I don't know exactly where that collision is going to take place. We could determine what that position would be, but what this does tell me, by assuming that the trains were on separate tracks and analyzing the motion of the trains separately, this does tell me that a collision will occur. And so our answer to the first part of the question is something like, since the final position XA is greater than the final position XB, the trains will collide. And so that's proof enough that there will be a collision. The next part of the question, if you remember, said that if the trains do collide, when do they collide? So essentially what that's asking is, from the moment that we've drawn in the picture here, when they are 950 meters apart, they begin applying the brakes. How long after that instant in time do they collide? And so in order to determine that, I'm going to use a different kinematic equation. The kinematic equation I'll use to answer that question is the second one that we derived, which was x equals x naught plus v naught xt plus 1/2 ax t squared. So I'd like to take a moment to just describe how I'm going to solve this last part of the problem. What I'd like to do is I'd like to take this equation, and just like before, I'm going to write this equation with the variables put in for each of the trains separately. But what I know now is that there's going to be a collision for sure. And so what that means for me is I can solve this for xa equals and xb equals. And I know now that because there's a collision, when the collision occurs, the two trains will be at the same location, which means that I can set xa equal to xb. And let's make sure we understand the distinction. In the first part that I just worked out in order to determine if there was a collision, I assumed that the trains were on separate tracks. And that meant when I solved for xa and xb, that meant they were able to stop on their own regardless of the other train. But since there will be a collision, I now know that I can set these final positions xa and xb equal to one another, the position when they collide, in order to solve for t, which is the time when they collide. And so now I need to input the information just as I did in the first case. So the initial position of train A is 0. The initial velocity of train A is 32, and it was positive, so 32t. And the acceleration of train A was negative, so I'm going to make the third term negative and write 1/2 0.8 times t squared. And for train B, the initial position was 950. The initial velocity was negative because train B was initially moving to the left, so minus 38t. And the acceleration was positive, so plus 1/2 0.8 times t squared. And these equations could be worked with just a little bit, I could write xa equals 32t minus 0.4t squared. And for train B, I could write 950 minus 38t plus 0.4t squared. And again, my method here is to set those two equations equal to one another and solve for time. So I would be solving for t at the instant where the two positions of the two trains is equal. And that's exactly what I want, the moment where that collision occurs. So this looks something like the following. 32t minus 0.4t squared equals, right? So that is this first equation on the left. And now the second equation is going to go on the right. 950 minus 38t plus 0.4t squared. And so there's lots of simplification that can occur here. I'm going to add this 0.4t squared to the right-hand side. I'm going to subtract this 32t to the right-hand side with this term. And what we'll find is that we will get 0 equals 950 minus 38 and 32 gives me 70t plus 0.8t squared. And so this is, if you haven't identified it already, this is a quadratic equation, right? If you're picky, I could write 0.8t squared minus 70t plus 950 equals 0. And so this is a quadratic equation in which the first coefficient is 0.8, the second coefficient is negative 70, and the third coefficient is 950. And so we should be able to use the quadratic equation in order to solve for t. Now, I am not going to write out all of the numbers into the quadratic equation. My calculator can solve for t here, but here the time that we want is, the t in this equation can be solved with the quadratic equation, which should be given by something like minus b plus or minus the square root of b squared minus 4ac all over 2a, where a is equal to 0.8, b is equal to minus 70, and c is equal to 950. And so given that, if you either solve that on your own or with your calculator, you should find, like any other instance where you've applied the quadratic equation, that you arrive at two answers. And in this case, the two answers that you will get is 72 seconds and 16 seconds. And so these are two different times that are both positive and maybe both are plausible. And so what do each of these two times mean? Whenever you're solving a problem like this, the correct time, the time that you want, is the smaller time, t equals 16 seconds. Because the answers to this quadratic equation are times when the positions of the two trains are equal. And so t equals 16 is the smallest time, which means that would be the instant where they collide. But the problem here is, and this is an interesting little piece of information when we're doing physics, is the equations that we used and the quadratic equation do not know that the problem we are solving is about two trains on a track and that they're going to collide, and that once they collide they can't keep going. So for instance, if the two trains were on separate tracks, you could imagine a situation where the two trains are moving toward one another, they get to the same spot after 16 seconds, they continue moving, and under their own decelerations come to a stop, and assuming that those decelerations, those accelerations that those trains have, continue to act on those trains, those accelerations would then bring those trains back to that same position again. And that is what that t equals 72 seconds represents. So t equals 16 seconds is the value that we want, but the t equals 72 seconds is also something physical and has meaning in this problem as well. It just isn't the value of time that we were looking for in this problem.